こになってしまえばきっとこの夏は充実するのもっともう戻れなくたって忘れないで
For our third topic, we have the water pollution and river. Under this, we will be talking about total maximum daily loads, or the TMDL, effect of oxygen demanding waste on rivers, biochemical oxygen demand, or also known as the BOD, the graphical determination of BOD constant, laboratory measurement of biochemical oxygen demand, additional notes on biochemical oxygen demand, nitrogen oxidation, straighter Phillips DOD sag curve. Then the last one is effect of nutrients on water quality in rivers. Objective of water quality: to control the discharge of pollutants so that the water quality is not degraded to an acceptable extent below natural background level. So we must be able to first measure the pollutants, second to predict the impact of pollutants on water quality, third is the determination of background water quality, and fourth to decide an acceptable level. So controlling waste discharge must be a quantitative endeavor. The impact of pollution in river depends on, first, the nature of pollutants. Second is to the unique characteristic of rivers. The most important characteristic includes volume, speed of water flow, depth, type of bottom, and surrounding vegetation. And the third one is the other factors. So under this, we have climate, mineral heritage, land use patterns, and types of aquatic life in the river. Now let's talk about the total maximum daily load, or the TMDL. A TMDL specifies the maximum amount of pollutant that a water body can receive and still meet water quality. So we have here the equation of the TMDL. TMDL is equal to the summation of WLA, which stands for the waste load allocation. That is portion of TMDL assigned to existing and future point sources, plus the summation of LA, which stands for load allocation. It's a portion of TMDL assigned to existing and future non-point sources, plus the MOS, which stands for the margin of safety. Effect of oxygen demanding waste on river. The introduction of oxygen demanding material, either organic or inorganic, into the river causes depletion of the dissolved oxygen in the water. To predict the extent of oxygen depletion, we have to ask two questions. The first one is how much waste is being discharged. Second one is how much oxygen will be required to degrade the waste. So the organic oxygen demanding material are commonly measured by determining the amount of oxygen consumed during the degradation in a matter approximating degradation in natural water. Biochemical oxygen demand. Under this, we're going to talk about THOD, COD, and BOD. So let's start with the THOD, or the theoretical oxygen demand. The theoretical oxygen demand, THOD, or the amount of oxygen required to oxidize a substance to carbon dioxide and water. It can be calculated by stoichiometry if the chemical composition of a substance is known. Chemical oxygen demand, or the COD, measured quantity that does not depend on the knowledge of the chemical composition of the substance in the water. In the COD test, a strong chemical oxidizing agent, or chromic acid, is mixed with the water sample and then boiled. It can be calculated by the difference between the amount of the oxidizing agent at the beginning of the test and that remaining at the end of the test. So we actually have several problems that we're able to solve in our previous lesson, so I'm not gonna give examples anymore. So for the biochemical oxygen demand, or the BOD, if the oxidation of the organic compound is carried out by microorganisms using organic matter as food source, the oxygen consumption is known as biochemical oxygen demand, or the BOD. So actual BOD is less than the THOD due to the incorporation of some of the carbon into the new bacterial cells. The BOD test is an indirect measure of organic matter because we actually measure only the change in dissolved oxygen concentration caused by the microorganism as they degrade the organic matter. So only on the rare circumstances will the THOD, COD, and the BOD will be equal. If the chemical composition of all the substances in the water is known and they are capable of being completely oxidized both chemically and biologically, then the three measures of oxygen demand will be the same.
So we have here the THOD problem. Compute the THOD of 108.75 mg per liter of glucose. So step 1 is to write the balance equation of the reaction. So here's the balance equation. And step 2 is to compute the gram molecular weight of the reactants. So we already know how to do this because we've discussed this in our previous lesson. So first is to know the molecular weight of each of the elements. So as we all know, we have carbon, it has a molecular weight of 12, hydrogen has a molecular weight of 1, and oxygen has a molecular weight of 16. Since we have 6 carbon, so we just need to multiply 6 to the 12, which is the molecular weight of carbon. And for the hydrogen, we have 12, so we have 12 hydrogen. For the oxygen, just multiply it with 16 because 16 is the molecular weight of the oxygen. So we have 6. We have multiplied 16 by 6, and that's 96. Now we have overall the glucose has 180 grams. So for the oxygen, we have 6 times 2 of oxygen, that would be 192. Thus, it takes 192 grams of oxygen to oxidize 180 grams of glucose to carbon dioxide and water. So now we need to get the THOD, the last step. So let's do this way. You just have to calculate it using stoichiometry. So 108.75 milligrams per liter of glucose. Have it close it in a parenthesis, and then you multiply it to 192 grams of oxygen over 180 grams of glucose. So using a calculator, just have to do it a little math. 0.75 192 divided by 180 is equal to, that's 116. Okay, so our answer is 116 milligrams per liter of oxygen. So that's it for our THOD problem. BOD rate equation. BODT is equal to LO times 1 minus 10 minus K na dako times D. So, where LO is the oxygen equivalent of organic compounds at time T. So, ang T na to is time na siya. Referred to as ultimate BOD. Ang kanang LO sa ubang sources or sa other book kay ginan siya as BODU or ultimate BOD. Ang K nga dako, kaya mo na siya used for constant in base 10. Pero usually po itong sa naging lesson, ang gigamit naman is K na gamay. So, mo na siya itong reaction-based constant in base E. Where K is equal to 2.303 nga dako. Okay, balang equivalent niya. So, para masabtan na ito, para asa siya magamit, usan siya paggamit, natay example na ipakita. So, we have here our problem sa katong equation ganina. So, the BOD3, if the BOD3 of a waste is 75 mg per liter, and the K siya na dako ha, K is 0.150, what is the ultimate BOD? So, ultimate BOD, diba? Mato siyang LO. Okay, so, gamit na itong formula ganina, while ago, itong BOD rate equation ba to?
Yes, ara, BOD rate equation mo na itong gamiton. So, first thing is, pangitaan dyan mo ang mga given. So, ang given nato diri natay BOD no kani BOD 3. So, ang BOD 3 daw nato is 75, which is kani gibutan siya diri sa BOD 3 nga place. Tapos natay K nga dako, ara. Ang value ni is 0.150, ibutang nato siya. Tapos ang di ba diri kay T man ni siya. So, i-times nato siya diri sa ang katong K nga dako i-times siya sa T. So, since ang T nato is 3, so 0.150 times 3, then automatic na siya na negative diri kay negative KT man to dito Okay. So if atong unahon ni siya kanay erase nato ning 10 sa answer ani, tapos 1 minus ang answer ani. Tapos mo ni siya. If 0.645 ang kani. Tapos ang kani siya, i-divide ni siya sa answer ani, which is katong 0.645. Tapos cancel mo siya diri, makancel po itong sa ilalom. So i-divide siya diri So mahimo na siyang LO or ultimate BOD is equal to the 75, which is katong BOD 3 nato over ang answer ani. So kung i-divide nato ni silang duha, ang answer ani kay ara 116 or 120. Okay? In base E, katong ganing giingon ako ganina, kay diri ang humang kag base 10, ibig sabihin K nga dako ang imong gamiton. Since K nga dako man ang na diri or given, so ang pinakauna nato is base 10 ato ang una nga formula. Actually, mag-arrive lang jud mo na sa same lang na answer if ever base 10 or even base E ang inyong gamiton. So for the base E, mo ni siya no. So since nakabutang dito ang mo ni ang formula to get the K katong base E. So, ang K is equal to 2.303 times katong K nga dako. So, times natin 2.303 sa 0.150. Tapos, ang answer niya is equal to 0.345. So, instead, sa formula, instead of ang gamiton diri at 10, pag sa base E, E ang gamiton. Okay? So, 75 gihapon, ang BOD 3 is equal to ang LO, mas ultimate BOD, which is pangita nato, times 1 minus E instead of 10, tapos raised to ang kaning answer nato diri which is small k, times same nga gihapon T, so KT magyapon siya dito So we're gonna arrive with the same answer of 116 or 120. So that's it sa to ang BOD rate equation na problem. So
the numerical value of the rate constant is dependent on the following. The first one is the nature of the waste. A second is the ability of the organism in the system to utilize the waste. And the third one is the temperature. So let's start with the nature of the waste. There are literally thousands of naturally occurring organic compounds, and not all of which can be degraded with equal ease. The BOD rate constant for complex waste depends very much on the relative proportion of the various components. The lower rate constant for treated sewage compared to raw sewage results from the fact that easily degradable organic compounds are more completely removed than less readily degraded organic compounds during the wastewater treatment. For a second is the ability of organisms to utilize waste. Any given microorganism is limited in its ability to utilize organic compounds. As a consequence, many organic compounds can be degraded by only a small group of microorganisms. The BOD rate constant is lower in the laboratory test than in the natural water when the culture used and inoculate the BOD test may contain only a very small number of organisms that can be degraded in a particular organic compound in the waste. The BOD test should therefore be conducted with organisms that have been acclimated to the waste so that the rate constant determined in the laboratory can be compared to that in the river. So temperature is the third one. Most biological processes speeds up as the temperature increases and slows down when the temperature drops. It's because of the oxygen utilization is caused by the metabolism of microorganisms. The rate of utilization is similarly affected by the temperature. Ideally, the BOD rate constant should be experimentally determined for the temperature of the receiving water. There are actually two difficulties with this ideal. The first one is often the receiving water temperature changes throughout the year. So a large number of tests would be required to define K. Second one is an additional difficulty is the task of comparing data from various locations having different temperature. So we have here the equation for the temperature of KT is equal to K20 times theta raised to T minus 20. Okay, for T, that's temperature of interest in degrees Celsius. That's for the KT, we have the BOD rate constant and temperature of interest. And for K20, we have the BOD rate constant determined at 20 degrees Celsius. While theta is temperature coefficient. This has the value of 1.135. So, tanaw nimo ang iyang temperature to know kung unsa nga value of theta ang gamiton. For the temperature of 4 degrees Celsius to 20 degrees Celsius, we'll be using the value of 1.135 for our theta, while we'll be using 1.056 for temperatures between 20 to 30 degrees Celsius. So let's go on to our example. The problem we have here is a vase is being discharged into the river that has a temperature of 10 degrees Celsius. So a while ago, no, atong gitan-aw diri so 10 degrees Celsius, which is the belong siya diri So ang bitong value ng theta is 1.35. Okay, take note of that. Continue. What fraction of maximum oxygen consumption has occurred in 4 days? The BOD rate constant determined in the laboratory and the standard condition is 0.1151. So ang kaning 0.115 mo na siya ang ato ang K20. Okay? So ipalagin lang nato. So, KT, so ang KT ang T man nato is temperature, 10 degrees Celsius, na siya diri and is equal to 0.115 times 1.135. Ang kaning 1.135, mo to ingan ako ganina nga, ang value sa atong theta is mag-vary siya if ang imong temperature kay lahi. I mean, it's either kani nga value, kay 10 degrees maan, or kani. So, since 10 degrees man siya, so kanina itong gamitin na theta raised to 10 minus 20. T minus 20 man. So, ang T man nato is 10. Munang 10 minus 20. So, ato lang siyang kani siya, negative 10. Ang kaning 1.135, i-erase nato sa negative 10. Multiply nato ani. So, nakoy lang ha. So, try na ko siya solve. Pag i-erase nato ang 1.135 sa negative 10, which is answer sa 10 minus 20, ang answer niya is 0.282. Tapos i-multiply nato siya sa 0.115, ang answer niya is 0.032, which is narito sa problem. Okay? Katong 0.032, mapalang to siya ang pag-determine nato sa BOD rate constant for the waste of the river temperature. So, karon na naman tay K, which is kani, atong gamiton tong formula nga naa ganina sa BOD rate equation, which is katong BODT is equal to LO times 1 minus 10 raised to KT. Or if base E siya, which is base E man ang situation diri, 1 minus E raised to KT. So, karon nanantay K, ang atong buhaton is, i-rearrange lang nato ang atong formula. Plugin nato si K, which is 0.032, times nato siya 4, since ang BOD man nato, no, kay, 4 days man. So, ang T nato is 4. So, times na nato siya. Napad ko separate na gisolve ana. Tanaw nato. So, ara kung separate na gisolve, ang BOD 4 over LO or ultimate BOD is equal to 1 minus E raised to katong 0.032, which is the value of K, times 4, the value of T or 4 days. Itong T, no? Tapos, pag ang E, erase na to sa answer sa 0.032 times 4 nga negative, ang magawas is 0.8799. Then, i-minus lang nato na siya sa 1. So, 1 minus 0.799 is equal to 0.12. Mo na siya ang ato ang fraction of maximum oxygen consumption during 4 days. And that's it for our temperature problem. The graphical determination of BOD constants. So the constants here are K and LO. The simplest and the least accurate method is to plot BOD versus time, which is mag-graph. So, muna ito ibutang. A hyperbolic first order curve. Ultimate BOD asymptote for curve K-rate equation. Method that linearize the data. So, we're gonna use the Thomas graphical method. Now, we're here to talk about Thomas graphical method. The procedure for determining the BOD constant by this method is as follows. So, the first, we have here several steps to follow in order to get our constants. First one is from the experiment result of the BOD for various values of t, calculate the t over BOD t raised to 1/3 for each day. Second is to plot t over BOD t raised to 1/3 versus time on arithmetic graph paper and draw the line of best fit by eye. Later on, para mas masabdan niyo natin example, which is ipakita na to ang each step. Then, the third one is to get or determine the intercept, which is represented by the letter A, the big letter A, and for the slope, it is represented by B. So, kaning duha, mo na siya itong pangitaon for our third step from the plot. Dito siya sa graph na tanawon. Okay? To get A is equal to K times LO, which is ultimate BOD raised to negative 1/3. And to get B is we have K raised to 2/3 over 6 times our ultimate BOD raised to 1/3. Okay, for our fourth, now we're here to get our K and LO to calculate our constants. So K is equal to 6 times B over A. B is our slope and A is our intercept. So yeah, 6 times slope over the intercept. And LO is equal to 1 over 6 times our intercept squared times our slope. So let's begin. And we have an example here. Determine the BOD constant. So for first step is from the experiment result of BOD for various value of t, calculate the t over BOD t raised to 1/3. So tanan na value nato or ang experimental result ato lang siyang i-solve gamit ani. Okay, ang t kay since ang t is time, so to erase at 1/3. So first is calculate the values of t mo na siya. And nana na dire ang mga values no for zeros, syempre wala. 1 is equal to 0.315, 2 is equal to 0.327, 4 is equal to 0.362, 6 is equal to 0.384, 8 is equal to 0.416. So muna na siya ang values atong t over BOD t raised to 1/3. And next step is to plot it versus time, arithmetic graph. So since muna na itong graph, so yan yung graph natin. Okay, so as you can see here, naadaan atong intercept no. Intercept nato or A is equal to 0.30. Since na-graph naman nato siya, using our graph, napangitaan na nato si A. So 0.30 mo na siya. Itong pinaka first part, okay? And B, okay? The plot of BODT versus time for this data is shown on this figure kani siya. From the figure, A is equal to 0.30 and B is equal to, since at na formula ganito, gamito lang nato siya, okay? So, ang atong formula sa B is ara, K raised to 2/3 over 6 times LO, which is the BOD, ultimate BOD, and raised to 1/3. Nahata sa pagkuha sa itong B. So, ang B is equal to 0.46. Mo ito siyang value sa kani katong ika day 8 na minus katong nagsugod na time Ano siya ang value nitong nagsugod pinakaunang part sa graph, which is kani. Then ang katong day 8 kay kani. So day 8 minus katong day 0. Day 0 di itong day 0. Itong pinakauna, which is kani. Kani jud muna siya. Minus tani mo siya. Tapos over 8, which is katong day man siya, itong 8 minus 0 is equal to 0.0145. Tapos, substitute lang nato siya, no? Dito sa pagkuha nato sa itong constant, na itong formula nato, which is kani. Mana itong formula sa K o sa LO. So, to get that, substitute lang nato si K is equal to ang value ni slope times mo sa 6 over katong value ni intercept. Mo na answer is 0.29. Mo na siya ato ang K. Now to get the ultimate BOD or the LO, it's equal to 1 over 6 times the R intercept, which is 0.30 raised to times our slope, which is 0.0145. So we have the answer of 1 to 8. So yeah, 1 to 8 or 30 mg per liter. So now we have the value of our K and our L. So that's it for our Thomas graphical method. So yeah, that's graphical method.
Laboratory measurement of biochemical oxygen demand. Step 1. A special 300 ml BOD bottle is completely filled with a sample of water that has been appropriately diluted and inoculated with microorganism. The bottle is then stoppered to exclude air bubbles, and the most oxygen it can be dissolved is about 9 mg per liter. So the BOD of the diluted sample should be between 2 and 6 mg per liter. Diluted with a special dilution water that contains all the trace elements required for bacterial metabolism and inoculum of microorganism. We have here the BOD bottles. The bottle on the left is shown with cap removed to illustrate the shape of the glass stopper. This one. The point on the end of the stopper is to ensure that no air is dropped in the bottle. The bottle on the center, this one, is shown with the stopper in place. Water is placed in a small cup formed with the lip. This acts as a seal to further exclude air. While the bottle on the right, this one, is shown with plastic wrap over the stopper. This is to prevent the evaporation of the water seal. So that's our BOD bottles.
The ratio of undiluted to diluted sample is called the sample size, usually expressed as percentage, while the inverse ratio is called the dilution factor. Mathematically, these are sample size is equal to the volume of undiluted sample over diluted sample times 100, where the dilution factor is equal to the volume of diluted sample over the volume of undiluted sample is equal to 100 over the sample size in percentage. The appropriate sample size to use can be determined by dividing 4 mg per liter by the estimated BOD concentration in the sample being tested. A convenient volume of undiluted sample is the chosen to approximate to this sample size. So now we have here a problem regarding sample size and dilution factor. The question is, the BOD of wastewater sample is estimated to be 180 mg per liter. What volume of undiluted sample should be added to a 300 ml bottle? Also, what are the sample size and dilution factor using this volume? Assume that 4 mg per liter of BOD can be consumed in the BOD bottle. So the first thing we need to do is to estimate the sample size needed. And to do this, we just need to divide kani ato ang gi-assume na pwede niya ma-consume over the wastewater sample. Ito gi-estimate nato, which is 180. Then i-multiply nato siya sa 100. So mukha nato ang answer is 2.22. Next step is to estimate the volume of undiluted sample needed, since the volume of diluted sample is 300 ml. So, na naman daan ang diluted sample. So, to get the volume of undiluted sample, we just need to multiply our estimated sample size needed to our diluted sample. Volume of our diluted sample, which is 300. So, we're gonna get 6.66 milligram milliliter. So, now, therefore, the convenient sample volume would be 7. So, why 7? Because So, gi-round off na to siya diri. So, 7 na itong gamiton to get the actual sample size and dilution factor. So, this time, kung ano na to, gamiton na itong formula nga naata ganina. Itong gipakita na ako. So, muna siya itong gamiton. And then, i-plug in lang na to. So, muna siya itong undiluted sample, no? So, sample size is equal to kani 7 over 300, which is our diluted sample, times 100. So, we're gonna have a sample size of 2.33%. Since naka-percentage form lang siya. Okay, ang dilution factor nato is ang dilution, the volume of the diluted sample, which is 300 ml over the undiluted, which is 7. This, atong answer there is 42.9. So, muna natong sample size and dilution factor.
Step 2. Blank samples containing only inoculated dilution water are also placed in BOD bottles and stoppered. Blanks are required to estimate the amount of oxygen consumed by added inoculum of microorganism called seeds, in the absence of the sample. Step 3. The stoppered BOD bottles containing diluted samples in blanks are incubated in the dark at 208 degrees Celsius for a desired number of days. For most purposes, a standard time of 5 days is used to determine the ultimate BOD and the BOD rate constant. Additional times are used. The samples are incubated in the dark to prevent photosynthesis from adding oxygen to the water and invalidating the oxygen consumption result. For step 4, after the desired number of days has elapsed, the sample and blanks are removed from the incubator and dissolved oxygen concentration in each bottle is measured. The BOD of undiluted samples is then calculated using the following equation. BODT is equal to DOBT minus DOST times the dilution factor, where the DOBT is equal to the dissolved oxygen concentration in blank after T days of incubation, while the DOST is equal to the dissolved oxygen concentration and sample after T days of incubation. So we have here an example. So we needed to recall, a while ago we've solved about sample size and dilution factor, and our result on the dilution factor is 42.9. So we're gonna use that to solve our BOD5 right now. So here's the problem. What is the BOD5, the wastewater sample of example 7? So this is what I'm referring to, the problem we solved a while ago. If the DO values of the blank and diluted sample after 5 days are 8.7 and 4.2 milligrams per liter respectively. So now we have here the solution. Just need to substitute everything on our formula. So BOD5, since we have 5 days, or 5T is equal to 5, is equal to 8.7 minus 4.2 times our dilution factor that we solved a while ago. So that would give us 193 or 190 milligrams per liter. So that's our BOD5. Additional notes on biochemical oxygen demand. Although the 5-day BOD has been chosen as a standard value for most wastewater analysis and for regulatory purposes, ultimate BOD is actually a better indicator of total waste strength. So I'll be showing you two graphs here. So the first one is the effect of K on ultimate BOD for two wastewater having the same BOD5. While the second is the effect of K on the BOD5 when the ultimate BOD is constant. Nitrogen oxidation. Nitrogen BOD or NBOD is the oxygen consumption due to the nitrogen oxidation. Nitrogen is released into the surrounding water as ammonia.
while the carbonaceous BOD or the CBOD is the oxygen consumption due to the oxidation of carbon. Normal pH, ammonia is in the form of ammonium cation. We also have the nitrification, which is the ammonia released from organic compounds and other sources. When I say other sources, it includes industrial waste and agricultural runoff. Oxidized to nitrate by nitrifying bacteria as their source of energy.